Section 5.6, the substitution rule. This is another rule. Sometimes we'll call this U substitution, like this, U substitution. Or U sub for short. And what this rule does is it essentially does the chain rule backwards. Because remember, we're learning how to integrate here, which is the reverse process of differentiation. Okay, so how do we deal with functions that, maybe we're integrating something that originally came from a chain rule being performed, right, to do a derivative? That's what we're trying to do here. So let's look at the definition, see some examples, and get used to how this procedure goes. We're going to let u equal g of x, where g prime is continuous on, whatever given interval we're working with, and let f be continuous on the range of g. Then we have that the integral, and for now we're just talking about indefinite integral, we're not worrying about limits of integration. The integral of f of g of x times g prime of x dx is just the integral of f of u du. We are dealing with compositions of functions here. And we are essentially letting u be whatever the inner function is. So you might remember when we were doing chain rule problems, finding derivatives, we always made this distinction of like, what's the inner function, what is the outer function? So in these problems, we are thinking of g of x as the inner function, and we are going to generally let u equal g of x. Let's take the derivative of both sides of this little equation right here so we can see where these other components come from. If I differentiate with respect to x, on the left side I'll have du dx, and then differentiating g with respect to x, just g prime of x. And I'm going to multiply both sides of this equation by dx to isolate du. So then du will be equal to g prime of x dx. Okay, notice that this, these two factors right here, the g prime dx, appears right here in the statement of this rule here. Okay, so oftentimes when we're dealing with integrals that involve compositions of functions, we're trying to find the derivative of the inner function within the integrand. Okay, so a lot of this is very abstract and vague. The best way to sort of come to know this process is by doing some examples. So let's look at this example and talk about a process that we go through to try and evaluate integrals that involve compositions of functions. So here is an integral of 2x plus 1 quantity raised to the 5th power dx. So this is an example where it's pretty clear. We can see the inner function and the outer function. The inner function is this, so I'll call that g of x, which is 2x plus 1. Okay, and then our outer function appears to be like x to the 5th. So let's look through this process, a few steps to use substitution to integrate. So we have to choose a substitution. Generally, we let u be the variable that, replaces x. And we set u equal to g of x, where g is the inner function. Then we want to find du, right? Because if we're going to go from integrating with respect to x to integrating with respect to u, we're going to end up with a du on the end rather than a dx. So trying to find that du is part of this first step here. Okay, and then after that, we want to rewrite the integral in terms of u and du. There should be no x's and no dx's left in the problem. Okay, and then we integrate with respect to u. If it isn't possible, sometimes we have to try a different substitution. So there might be some trial and error here. And then once we're able to deal with that problem in terms of u, we back substitute and get it back in terms of x. So the process, really what we're doing here is like, we'll have a difficult problem in terms of x, and this is very common in mathematics. You know, we'll have like some kind of hard problem, and we're trying to find our way to the solution. And what we're doing with this process of substitution is we're sort of transforming this problem into an easier space, right? So it's like we transform into an easier space. And then we have like an easier solution. Which we then transform back into the original space. So transforming into u, solving the problem in terms of u, and then translating our answer back in terms of x. Okay, so, you know, back to this function, or this integral of 2x plus 1 to the fifth. Let's see how we would apply these steps to evaluate this integral. So first of all, we want to let u be the inner function. That's pretty standard. So then what is du going to be? So I always do this where, okay, we have u equals 2x plus 1. And then we take the derivative of both sides. So du dx is going to be equal to, what's the derivative of this with respect to x? It's just going to be 2. And then I solve for du. So then du equals 2 dx. Okay, so that's how these problems tend to start. And now let's look to our integral that we're trying to evaluate. So we want to know, what is the integral of 2x plus 1 to the fifth dx? I want to express this in terms of u because how would I evaluate this otherwise? You know, I don't have a chain rule for integration, really, like that's what we're trying to discover here. So the only alternative would be like multiply this whole thing out, like raise it to the fifth power, you know, and FOIL it out, and it would be an insane multiplication problem and isn't reasonable to evaluate this directly. So how do I write this all in terms of u? Well, u is just equal to 2x plus 1, and du is equal to 2 dx. So I can take this information and I can replace 2x plus 1 with u. So then it'll be u to the fifth. And now how about dx? What am I going to replace with dx? Well, I know that du is equal to 2 dx. So if I just solve for dx here, I can divide both sides by 2. So then I get du over 2 is equal to dx. So I'm going to substitute in du over 2 for dx. Okay, so then I'll end up with du over 2, like that. Okay, and now let's deal with this problem in terms of u. This 2 in the denominator, this is just a factor of 1/2. I can bring that to the outside of the integral. So then I just have 1/2 times the integral of u to the fifth du. And this is actually a pretty easy integral. You know, what's the antiderivative of u to the fifth? It would just be u to the sixth over 6 plus c, since we are looking at an indefinite integral here. Okay, and then I could distribute in that 1/2 if I wanted to. So I could write this as u to the 6th over 12 plus c over 2, but I can just leave it as c because c is just a constant value. If I divide it by 2, it's just going to be another constant value. So here is my answer in terms of u. The last step is just substituting in, what was u after all? I want to express this in terms of x. Well, I would just substitute in 2x plus 1 for u. So here's what I get. 2x plus 1 to the 6th power over 12 plus c. And that is my answer. Okay, notice that I could check my work if I wanted to. I could check by just taking the derivative, what's d dx of my answer, 2x plus 1 to the 6th over 12 plus c. What happens if I take this derivative? I'm hoping that I get 2x plus 1 to the 5th. Let's see what happens. Okay, so taking the derivative of this first term here, it's going to be a chain rule, right? Because I can leave the 1 over 12 on the outside for now. The inner function is 2x plus 1. The outer function is x to the 6th. So I would bring down the 6, and then I'd have 2x plus 1 to the 5th. So that's the derivative of the outer function around the inner function. And then times the derivative of the inner function would be times 2. And then plus c, constant goes to 0 when I take a derivative. So simplifying, I have 6 times 2 and then times 1/12. So that just simplifies to 1. And then I'm just left with 2x plus 1 to the 5th, which is, of course, what we started with. Right? This was the integrand in the beginning of the problem. So it worked. Okay, so that is our basic process for using u substitutions to evaluate integrals involving compositions of functions. Let's try another one. Example 2. We want to integrate this x cubed times 2x plus x to the 4th raised to the 5th power dx. This is a pretty scary looking one. We have a product, we have a binomial raised to the 5th power. One thing that indicates that I might want to use a u substitution on this problem is if I have stuff like this, products and compositions, that's one thing, because otherwise how would we deal with this integral? Again, it would be multiplying out this binomial 2 plus x to the 4th times 2 plus x to the 4th times 2 plus x to the 4th. 5 times. I would spend all day multiplying that out. So it isn't reasonable to, just kind of brute force multiply this out so that I can use a bunch of power rules. That isn't a very reasonable path forward. So I'm going to try a u substitution. And, this x cubed is making me a little nervous out here, but let's just try it. Let's see what happens, if I want to use that as my inner function. Generally, if there's something being raised to a power or, something that's kind of standing out as an inner function as we've come to understand them, I'll try doing a u substitution. So let's see, if I let u equal that inner function 2 plus x to the 4th power. Okay, I take the derivative, so then du dx is equal to the derivative of this, which is 4x cubed. And, ultimately I'm trying to replace dx with something in terms of u, so dx, something in terms of du. So I'm going to solve for dx in this equation. I would multiply both sides by dx, and then I could, divide, and here's what I'm left with. So du is equal to 4x cubed times dx, and then divide both sides by this. So then I get du over 4x cubed is equal to dx. All right, so this is generally how I proceed. I want to know what is u equal to and what is dx equal to. That will now allow me to do the substitution. So let's try to substitute this in and let's see what happens, because remember, we need all of the x's to go away. That's the challenge here. So this x to the third stays the same. I'm going to put in u for 2 plus x to the fourth. That was my plan. And in for dx, I'm going to put du over 4x cubed. Okay, just substituting in for this and this. And something nice happens. Because remember, I was having a bit of anxiety about this x cubed because I was, I don't want there to be any x values left over. I'm trying to get this whole problem entirely in terms of u. And we get a nice cancellation. This x cubed cancels with this x cubed down here in the denominator. That came from finding dx in terms of du. So we're left with this, the integral of u to the fifth du over 4. I can bring that 1/4 on the outside, and I have a really nice integral, just u to the fifth du. So we got kind of lucky on that one, but this is something that happens, and as we gain experience, we'll be on the lookout for this type of thing, because the reason why this x cubed canceled out is because the derivative of our inner function was, it basically had an x cubed in it. The derivative of the inner function was 4x cubed. So oftentimes, I'll be looking at a problem and I'll see what my inner function is, and I'm already thinking, what is the derivative of that? Is that derivative going to cancel out? Like, does it appear anywhere else in the integral? And in this case, it did. Okay, so all is well. Let's do this integral. So 1/4, and then antiderivative of u to the fifth is u to the sixth over 6 plus c. Remember, we always do the plus c if it's an indefinite integral. So I get u to the sixth over 24 plus c, just multiplying in that 1/4, and the last step is get it in terms of x, so I'll plug in for u 2 plus x to the fourth to the sixth over 24 plus c. All right, so that's a pretty impressive looking answer. Right? This process is really, really effective, right? This is a super difficult integral, but by just rewriting it, re-expressing it in terms of u, we're able to create an easier problem for ourselves and solve the problem in that space. Let's try another one. Example 3, here we have a quotient. Remember, we don't have a quotient rule for integration. We have one for differentiation, but we don't have one for integration. So whenever I see a quotient inside of an integral, I'm thinking, how am I going to deal with this? Am I going to multiply it out? Am I going to simplify it? Is there anything algebraically I can do to get out of this situation? Because, we don't have a fixed rule for how do we deal with a quotient. Multiplying it out in this case is not going to help us. Then we would just have, a quotient with an expanded out polynomial denominator. It doesn't really get us any closer to something that's easy to integrate. This is another scenario where we might consider doing a substitution. Because what if down here, like this x squared plus 1, what if I substituted in a u for that? And, what's the derivative of this? Am I going to get a cancellation with this x up here. Like that x is sort of that remaining factor. Like, will that go away? Like, am I going to get lucky if I do a u substitution? There's only one way to find out. Let's let u equal x squared plus 1. And we'll take the derivative, du dx is going to be 2x. Okay, I'm happy to see that it's just 2 times x, because maybe I'll get a cancellation with that x that's in the problem. But let's keep going. Now I just want to solve for dx is kind of the move, so I'll get du over 2x is equal to dx. That's what happens when I solve for dx. So let's try this out. Let's try the substitution, see if it's effective. So in for x squared plus 1, I'm going to put u. So it'll be x over u squared. And then in for dx, I'm going to put du over 2x. Again, just grabbing from right here and from right here. And does a nice thing happen? Yes. The x's go away. And I'm left with the integral of 1 over u squared du, and then I'll put the 1/2 out in front. I'm in the habit of, bringing that scalar multiple out in front of the integral. And this is a really nice little integral in terms of u. I'll rewrite this as u to the -2nd power, just setting it up for a power rule. Antiderivative, I'll add 1 to the exponent, so it'll be u to the -1st, divide by that new exponent, and put the plus c. So I'm getting, if I distribute in or multiply in that 1/2, I'll get -1 over 2u plus c. And then just substituting in for u, 1 over 2 times x squared plus 1 plus c. Okay, so very similar process, looking at each of these. It's just a matter of picking an inner function and seeing if it works out. Now, one thing I'll say about example 3, sometimes I'll get questions like, how do I know 2x plus 1 should be u? Like why not let u equal, I meant x squared plus 1. Why not let u equal that whole denominator, x squared plus 1 squared? Well, you could try it and see what happens. It's not going to work out in this case, but the reason why I didn't go down that road is because I was thinking about this thing where, the derivative, like in the previous example, it's like you want the derivative of your inner function to be canceled out by something that's in the integrand. So when I was looking at this problem, I sort of was thinking, if I let u equal x squared plus 1, if I take the derivative of that, there's going to be a factor of x, which will cancel with this one. Okay, so when picking your inner function, it makes sense to sort of scan the rest of the integrand and think, does the derivative of the inner function appear anywhere in the problem where it'll cancel out so that I can get the whole thing in terms of u, like I want to. Okay, so you'll gain experience and you'll be able to spot these kinds of things, but also it just takes some trial and error. If one substitution doesn't work, you might try a different substitution. Let u be something a little bit different. Try it out, see if you can make it work. And then sometimes there are little curveballs. Example 4 is one of those situations. We're looking at an integral, indefinite integral, x over the square root of 1 minus x dx. Okay, it doesn't look like too different from the last example, so maybe I'll try something sort of similar. Maybe let 1 minus x be my u value, so How about u equals 1 minus x? And then, so the derivative du dx is going to be just -1. So what we'll end up with is, solving for dx, negative du equals dx. Okay, so I'll take this, and I'll take this, and let's make the substitution. So this is the integral of x over the square root of u, and then negative du is what I'm substituting in for dx. Okay, I'm not entirely happy with what I see because look, the x here is left over. Like it didn't cancel out. I didn't get like a x in the denominator of this substitution over here. So what do I do? Well, I could try a different substitution. I could try letting u equal the square root of 1 minus x instead of just 1 minus x. That's not going to help, unfortunately. That's going to make things worse. But here's a little trick. If I take this, so we let u equal 1 minus x, notice that I can actually solve for x in this equation. Like if I add x to both sides and subtract u from both sides, I get that x is equal to 1 minus u. So I can actually take x and replace it with 1 minus u. Right? So this is the substitution that I'm going to use next. This is like kind of a little substitution within the substitution. I'm going to put in for x 1 minus u, and then I'll have divided by the square root of u. And yeah, negative du, maybe I'll just put the negative out in front and just have the du right here. That looks pretty nice. Okay, is this any better? It actually is, because when we have a difference, a sum or a difference in the numerator of a fraction, we could split that fraction up into multiple terms. So I can rewrite this as 1 over the square root of u minus u over the square root of u du. And this is good. We tend to have a preference for, a bunch of individual terms. Again, like quotients, stuff like that. Can be a little bit difficult with integration. But now that we have a couple of terms and I can rewrite them, this one I could rewrite as u to the negative 1/2 power. That's good. That's set up for a power rule. This one I can write as u to the positive 1/2 power. And that's because, this is u to the first divided by u to the 1/2. So there's this rule of exponents, property of exponents. This is u to the 1 minus 1/2. You take the difference of those exponents. And this is just u to the positive 1/2. Okay, so that's where that came from down there. And du. And this looks pretty good. I can totally evaluate this. I could get antiderivatives. This is going to be u to the positive 1/2 times 2 over 1. So that was adding 1 to that exponent and multiplying by that exponent. And over here we'll have u to the 3/2 times 2 over 3. And we'll have a plus c on the end. Keep working over here. Simplify a little bit. I'll distribute in that negative that we have out in front. I'll get negative 2 square root of u plus 3 over 2, and then u to the 3/2, you could write this as square root of u cubed. You could do that if you want, plus c. Okay, so I was just simplifying. I distributed that negative. I don't bother making this a negative c. It doesn't matter. C is just some constant, any constant value. And the final step is getting it back in terms of x. So substituting in 1 minus x for u, I get negative 2 square root of 1 minus x plus 3 over 2 square root of 1 minus x cubed plus c. And yeah, that looks good. I think that's simplified enough. I'll box it up. That's a pretty intense answer, right? Like, if I showed you this at the very beginning of this chapter when we were just learning how to do antiderivatives, you'd think it'd be impossible to come up with an integral, an answer like that. But it's really pretty straightforward once you get the practice and just get used to the little tricks using u substitutions to evaluate these tricky integrals. All right, so the main curveball on this one is just this little portion right here. Sometimes you have to do a little trickery to eliminate a stubborn variable that's stuck in your integrand x that you'd like to get in terms of u. You could do something like that. All right, so we've been dealing with just indefinite integrals so far, so no limits of integration, just doing the substitution and the anti-differentiation. What if we have a definite integral? Okay, so something like this, where we might use a u substitution, but we have limits of integration that we have to deal with. Okay, so all that we really have to do is we also have to transform the limits of integration into the u space, or the universe, as I sometimes call it. Okay, so you'll notice that this property, or this, this statement of the rule right here, looks pretty much identical to the one that we saw at the top of the section, but now we just see that a and b, our limits of integration, are going to be evaluated at g, and that's going to get us into that universe. Makes a lot more sense when we actually see some examples, so let's work towards that. There are a couple different ways that we could deal with limits of integration. Option one is using the same rules as before and then back substituting and using the original endpoints in the fundamental theorem of calculus, like when we actually go to evaluate it, because remember, when we evaluate an integral, a definite integral, we do that thing where we find the antiderivative and we plug into the antiderivative f of b, and then subtract from that antiderivative evaluated at a. Okay, so one option is that we back substitute, at the end of the integration and the u substitution, go back in terms of x and then proceed that way. But option two, and this is a nicer way of doing it, it's a little more efficient, is we actually transform the endpoints as well. Okay, so let me show you what that looks like. For example 5, we want to find this integral from negative 3 to 0 of 2x plus 6 to the 4th power dx. So first impressions of this, it's a composition. I don't want to multiply that out. I'm thinking a u sub is going to be helpful here. So I would be looking at, this 2x plus 6 as being my u value. So I might start by saying, okay, let's let u equal 2x plus 6, and then going through the normal motions, take the derivative of both sides, du dx is just going to be equal to 2. And then solving for dx in this, I'll get du over 2 is equal to dx. Okay, so the substitution part for the integrand is kind of taken care of. That's going to be my u, and that is what's going in for dx. Now, how about the limits of integration, though? Because we have negative 3 and 0. So those are x values. All right, so over here, I'm going to say, all right, I have my limits of integration. And I have two of them. I have x is equal to -3 and I have x is equal to 0. These are x values. I would like to make them u values. And it's actually pretty straightforward. U is just going to be equal to 2 times -3 plus 6, right? So see how I'm just plugging into my formula for u. So simplifying this, what do I get? 0, right? -6 plus 6. And then if I put in 0, 2 times 0 plus 6, this just becomes 6. So now I have my limits, my new transformed limits of integration 0 and 6. So I'm going to put a little cloud around this whole thing. And now here's what my transformed integral is going to look like. So yeah, on the inside, I'm going to have u to the 4th, and then du over 2 goes in for x. And my limits of integration are going to be not -3 to 0, but 0 to 6. All right, so here's the really nice thing about transforming the limits of integration. I can go about integrating this. All right, so I'll pull out the 1/2, and I'm going to do an antiderivative and all the stuff that we normally do. At the end of the problem, when I finish doing this, I am not going to have to go back in terms of x. Since I transformed my limits of integration, I can just sort of like carry out the process as I normally would. You know, so I got an antiderivative of u to the 5th over 5. My limits of integration are 6 and 0. I'm just going to plug in 6, so, 6 to the 5th over 5. And then subtract from that 0 to the 5th over 5. And I'm left with, 6 to the 5th power divided by 10. That's what it'll simplify to. And I put this into my calculator and got 777.6. All right, notice that there's no need to go back in terms of x. Right? Everything is taken care of. Like when I get to this point where I have my antiderivative in terms of u, I don't have to go back in terms of x because my limits of integration are u values. So I can just substitute directly in and finish out the problem as I normally would if I was just working in terms of x. Okay, so this option 1 is if we don't do this. Like if we don't do this and we're just left with x equals -3 and x equals 0 as our limits of integration, in that case, we would have to then, transform this back in terms of x, and then we would substitute the x values back in. And in my opinion, it feels like a little more work. The flow of the problem gets disrupted a little bit. I would much rather just deal with it in this way where I transform my limits of integration at the same time that I'm transforming everything else in terms of u. And then just let the problem sort of write out, do the fundamental theorem of calculus, and there isn't too much difficulty or sidetracking. So let's try another one. Same kind of process. Example 6, we're looking at the integral from 0 to 7 of the square root of 4 plus 3x dx. All right, this is a situation where we're kind of stuck here. We have a composition of functions. There's no multiplying this out. There's no, I can't really do anything to this to avoid using a u substitution. So this is a scenario where we must use a u sub. So let's try it out. Let's let u equal whatever the inner function is. I'm thinking 4 plus 3x. So then du dx, taking the derivative of both sides, is just going to be 3 So if I solve for dx, I'll get that du over 3 is equal to dx. So that's good, you know, I'm substituting u in for that, and then that's what's going in for dx. Let's do my limits of integration. So off to the side, I have x equals 0 and I have x equals 7. So let's get x equals 0 in terms of u. So u is going to be 4 plus 3 times 0. I'm just getting 4. And how about for 7? So 4 plus 3 times 7, it's going to be 21 plus 4. I'm getting 25. All right, good. I'll sort of put that in a bubble. And let's rewrite this integral. Now we will be integrating from 4 to 25. And the integrand is just the square root of u du over 3. That's what we're left with after doing all of those substitutions. I'll bring the 1/3 on the outside. I'm kind of in the habit of doing that. This is u to the 1/2 power, so the antiderivative will be u to the 3/2, and then multiply by the reciprocal of that new exponent, 2/3. And I'm not going to put the plus c because it's a definite integral. I just have to evaluate at 25 and 4 and take that difference. So I'll do that next. 1/3 times, okay, plugging in 25. So 2/3 times 25 to the 3/2 minus 2/3 times 4 to the 3/2. Or sorry, 2/3. No, to the 3/2. Too many fractions. Okay. And raising to the 3/2, it's just take the square root and then cube it. So this is really 2/3 times 5 cubed, which is 125, minus 2/3 times 8. That's what we're left with here. Okay, and then you could simplify this however you deem fit. I'm inclined to pull out this 2/3. I could write this as 2 over 9, and then just 125 minus 8. I don't know. I don't want to deal with multiplying out more fractions than I need to. So 2 over 9 times, I'm getting 117. All right, and then multiplying, this is just 234 over 9. Or you could put into calculator or simplify if you're really good at division. You get 26. And that's our answer. All right, so another u substitution where we have a definite integral. It's as simple as just transforming those limits of integration and doing the problem as you normally would. It's just in terms of u instead of in terms of x. How about example 7? Integral from 1 to 2 of x squared over x cubed plus 1. Man, I've done too much math today. X cubed plus 1 quantity squared dx. Okay, I'm thinking definitely u substitution. Just seeing that we have a quotient and composition, like this is kind of just screaming u sub. Another thing that really makes me think a u sub is going to work is if I let that be my inner function, what's the derivative of that? 3x squared. I have an x squared in the problem for that to cancel with. Okay, so again, kind of looking out for, thinking ahead. What's going to happen if I let u equal x cubed plus 1. Is that going to jive with the other things, the other factors in this problem? I think it is. So taking the derivative, solving for dx, and what are my limits of integration? Well, I had x equals 1, so then u is going to be 1 squared, whoops, u is going to be 1 squared plus 1, so 2. And then x equals 2, substitute that in, u is going to be 2, sorry, this should have been cubed, 2 cubed plus 1, which will be 8 plus 1, which is 9. So here is my transformed integral. It'll be the integral from 2 to 9 of x squared, I'm thinking that's going to cancel out, over u squared times du over 3x squared. Okay, so that was just making the substitutions. And a good thing happens, the x squared cancels with the x squared, and yay, we ended up with everything in terms of u. That's what tells us we are successful. And even better, it's something that I know how to integrate. I'll write this as u to the negative second power, because I want to do a power rule. Oh, sorry, I forgot the 1/3. Right, the 3 in the denominator did not cancel out up there, so I have to include that. Okay, 1/3 times, and now let's do the antiderivative. I think I'm going to get negative u to the negative first power. And we're evaluating from 2 to 9. Or I might write that as negative 1 over u, like that. Okay, let's substitute in those values. So 1/3 times negative 1 over 9, using plenty of grouping symbols here, and then subtract from that negative 1 over 2. Being very careful about all those negative signs, so I'll have 1/3, and then it's going to be negative 1/9, and you know, to get a common denominator maybe of 18, negative 2 over 18 plus 9 over 18. I'll get 1/3 times 7 over 18. And that just simplifies to 7 over 54. And that's as simplified as that gets. I'm just going to box that up. That'll be my answer. All right, let's try this next one. We've made great progress. Just a couple pages left, I think. Example 8. Integral from 0 to 3 of 3t times the square root of t plus 1 dt. All right, this problem's in terms of t. It's going to behave in the same way as if it was in terms of x. How do we want to approach this one? Well, again, I see product, I see, a binomial inside of a square root. So that's like a composition of functions right there. Does it simplify nicely? Can I get this to, break down in such a way that it makes it easier to find an antiderivative? Not in terms of t. So I'm going to rely on a u substitution. So I guess let's try t plus 1. So let's let u equal t plus 1. So then du dt is equal to just 1. So du is equal to dt. Okay, kind of simple and nice. Let's transform these limits of integration. So t equals 0 and t equals 3 are the limits of integration. So u is just going to be 0 plus 1, so 1, and then the limit of integration 3 is just going to be 3 plus 1. So as a u value, it will be 4. Okay, so there's that. Let's see what happens when I make those substitutions. So now we're integrating from 1 to 4 of 3t times the square root of u. And then dt just simply gets replaced by du this time. And I'm left with this. Am I happy with that? There's an issue. There's an issue. We have a t left over. So you might look at this and think, oh no, it didn't work. This is a failed attempt at a u substitution. We have to scrap this plan and do something else. But remember, you should always check, can I express t in terms of u? So look over here to your initial substitution. And this is one of those scenarios where we can. If I take this, I can solve for t, and I get that t is equal to u minus 1. Okay, so this is like the final part of our substitution. So I'll do this. This will be the integral from 1 to 4 of 3 times u minus 1 square root of u du. And now you're probably thinking, God, is that really any better than what we started with? Like these look pretty similar. The variables change. Sure, it's in terms of u now, but is that actually easier to integrate? It is. We don't like having a sum or a difference inside of a radical because that sort of locks that sum or difference up inside of there. Similar to how we're generally not a fan of having like a sum or difference in a denominator. Okay, you can't really break that up and break it into a list of terms, which is obviously our preference when we're trying to integrate. So rewriting it in this way, where now we have this difference which is not inside of the radical. This is an improved situation because now we can do this. Let me show you how I would proceed from here. I'll bring the 3 on the outside just because why not? And first I'll rewrite this u square root of u as u to the 1/2 power. And I'm going to distribute this in here. I'll get 3 times the integral from 1 to 4 of u to the 3/2 power minus u to the 1/2 power. Again, just using properties of exponents to multiply. And now this is an integral ready expression. Take the antiderivative of u to the 3/2, I get u to the 5/2, and I multiply by the reciprocal of that new exponent, so 2 over 5 is the factor. Minus, this one's going to be 2/3 u to the 3/2. And I'm not going to put the plus c because this is a definite integral, I don't need it. Integrating from 1 to 4, so here it's time to substitute in. So plugging in 4. And then plugging in 1. One to any power. It's just going to be 1, so it simplifies like that. And then, yeah, just yet another really challenging expression to simplify, but we can do it. This will be 2/5, and then 4 to the 5 halves. Take the square root and raise it to the 5th. So 2 cubed is, 2 to the 5th power is 32. Minus 2/3. That becomes 8. Minus, and then over here I could get common denominators, maybe common denominator of 15. So this would be 6 over 15 minus 10 over 15. And I'll keep working up here. I keep writing too big. I don't think I write this large if it's a normal piece of paper. All right, and just keep grinding here. Multiplying 2/5 and 32. Distribute this negative. And then from here, I would get common denominators. I think 15 is going to be my common denominator here. So I'm going to spare you the rest of the work. We're left at the end of this with 1/16 over 5. That's how everything simplifies. And I'll box that up as my final answer. So example 8 is a real doozy. It's kind of a combination of all the trickiest scenarios where we would use a U substitution. So it's a definite integral, so we had to transform our limits of integration. That's what we're doing here. And we were stuck with this leftover t value that didn't go away, so we had to do that little trick where we solve for the original variable in terms of U and make that substitution there. And then a very challenging integral in terms of the arithmetic we had to do, but just work slowly, carefully, check your work after every step, and we should be left here with 1/16 over 5. How about we try an application? Example 9, and I believe this is the last page of the chapter, so let's go out with a bang here. The manager of a sporting goods store determined that the price in dollars, P, for each tennis racket is changing at a rate of P prime of X. So this is the rate of change of price, and we have this function here, negative 300x over x squared plus 9 to the 3 halves. Oof. Okay, and this is when x 100 rackets are demanded by customers. When the price is $75 per racket, 400 rackets are demanded. Okay, and we want to answer some questions. The first thing is we want to find the price function. So notice what we're looking at here is an initial value problem. Like, we are given a differential equation. Okay, so just to point out a couple things, this is an initial value problem. Okay, so we dealt with these at the beginning of the chapter, so I'll say, see section 5.1. But you might recall, what we do in this case is, like, we're given a differential equation, we're given the derivative of the price function, and we want to find the price function. So we're going to do that by anti-differentiating. And when we anti-differentiate, we're left with that plus c on the end, which is kind of like, there was some constant value here, and this is a bit of information that was lost. And we can only recover that lost information by using a data point that's provided. And that's what these values are. So it tells us when the price was $75 per racket, 400 were demanded. So this is really giving us an ordered pair. This is like our initial value. And the ordered pair is, now careful here, the x coordinate is measured in hundreds of rackets. So 400 rackets are demanded. What is the x value associated with 400 rackets? 4. So the x coordinate is 4, and then the price, and I think this is just measured in terms of dollars. Yeah, price is in dollars. So then the p coordinate is just going to be 75. Okay, so this is an initial value problem. Now it's time to find the antiderivative of this expression right here. So let's jump into this. P is going to be equal to the integral of p prime of x dx. So we're going to want to integrate negative 300x over x squared plus 9 to the 3/2, which is kind of a beastly integrand. But let's be brave and face it and see if we could figure it out. Yeah, definitely thinking we're going to need to use substitution. We've got a quotient, we've got composition, x squared plus 9. That's looking like a pretty good inner function. Let's try it. Let's see if we can let u equal x squared plus 9. And take the derivative, du dx is going to be 2x. I like that x is appearing right here because remember I have a x up here that I'm hoping to get a cancellation with. So things are looking pretty decent. Solving for dx, du over 2x is going to be equal to dx. This is an indefinite integral, so I don't have any limits of integration to transform, so I'll be able to stop here and just hope for the best. So I'll put u in for x squared plus 9, and then there's my du. Let's see what this looks like. Yeah, let's see. We'll do this integral negative 300x over, and now we're just going to have u to the 3/2, and in for dx goes du over 2x. The x's cancel out, yay! And we'll keep going here. That negative 300 over 2, I think I'll just, we can simplify that. That simplifies to a negative 150. So let me keep working over here. I'm just going to simplify. So negative 300 over 2 is negative 150. I'll bring the negative 150 on the outside of the integral. And left on the inside is just 1 over u to the 3/2, or I'll just write that as u to the negative 3/2, setting up for a, anti-differentiation power rule. du. All right, just looking over my work, making sure everything looks good. I think we're okay. Now we'll do the antiderivative, negative 150, and this is going to be u to the negative 1/2, so that's adding 1 to the exponent, and then multiply by the reciprocal of that new exponent, so times negative 2. And I have to do a plus c here because it's an indefinite integral. So simplifying a little bit, I can write this as 300 divided by the square root of u plus c. And then from here, just one last thing. We want to get this back in terms of x. So I'll just substitute in for u. So I'll have 300 over the square root of x squared plus 9 plus c. So there is the antiderivative, but we're not done yet because we need to figure out what is c. Okay, so that's the last part of this problem. We're going to use the initial value, and I'll just work right here. So the last part, so now we just want to use this ordered pair 475 to find c. So let's try this. I want to set p of 4 equal to 75. Right, so I'll be substituting in 4 for x. So I'll have 300 divided by the square root of 4 squared plus 9 plus c, and that's equal to 75. 4 squared is 16, plus 9 is 25, so this simplifies to just 300 divided by 5 plus c is equal to 75. So that's nice. It looks like we're getting sort of a whole number here. So 300 divided by 5 gives me 60. And then subtracting 60 from both sides, I'm getting that c equals 15. So finally, p of x, our price function, is this: 300 divided by the square root of x squared, zoom in a little bit, x squared plus 9 plus 15. Alrighty. You can check your work here. You can totally check your work by taking a derivative of this answer right here. Okay, and you'll do that and you'll find that you get this, which is the function we were originally handed. Okay, but assuming that's correct, moving on to part B, now we want to answer some questions. Hopefully we can do so using this function we just found. So part B, it says, at what price will 440 rackets be demanded? So we're given a number of rackets, so an x value, essentially, and we want to plug into our function and figure out what the price is associated with this value. So first of all, 440 rackets is associated with what t value? Or excuse me, x value. Well, x is measured in hundreds of rackets, so this would be 4.4. Okay, so what we're trying to do here is we want to evaluate p at 4.4. So we want to find p of 4.4. So we'll substitute in. Sorry, this should be plus 15. Okay, I put this in my calculator and I got approximately 71.33. And what are the units of this value? This is from our price function, so this is in terms of dollars. So the answer here, the price associated with a demand of 440 rackets is $71.33. So I'll box that up. And now for part C, what we want to do is, we're given a price this time. We're asked for, what is the associated production level or demand associated with this price. So here, we're going to use our function, our price function again. We are going to set P of X equal to 90. And this time, we're solving for the demand, the number of units rather than the price. So let's do this. I will plug in my function here. So 300 divided by the square root of x squared plus 9 plus 15, and we're setting that equal to 90. Okay, so 90, I'm going to take away 15 from both sides. So I get 75 over here. And I think I'll multiply both sides of the equation by square root of x squared plus 9, and I'll divide 300 by 75. So then I'll get this. Okay. 300 over 75 is just 4. So 4 is equal to square root x squared plus 9. I'll square both sides of the equation, and I get, 16 is equal to x squared plus 9. I'll subtract 9 from both sides. 7 equals x squared. And taking that square root, I would get a plus or minus here, but I'm talking about the number of rackets being demanded, so I'm just going to use a positive value. So I get approximately, or here I guess I'll write square root of 7 is equal to x. So x is approximately equal to 2.65. I'm going to round it to the nearest hundredth because I want to multiply this number by 100 to get the actual number of rackets, because x is measured in hundreds of rackets. So my answer is about, so I'll say approximately 265 rackets. Very good. And that brings us to the end of this example here. Initial value problem involving, a price function using use substitutions and then working with the function that we find. Answer a couple additional questions. And that brings us to the end of this chapter. So we've seen most of the techniques that we're going to use for integrating anti-differentiation. In the next chapter, we're going to start working with exponential and logarithmic functions. We're going to learn rules for differentiating, integrating. We're going to see a bunch of applications. So I'll see you in chapter 6 on exponential and logarithmic functions.